Okay, so we can officially start the second day of our quantum machine learning workshop. So, yeah, Jacob, the Zoom is yours and we can continue.
Thank you, Pablo. Welcome back to the second day. Today we have two sessions. One session is focusing on uh, creating classification models, and the second session will be more advanced on hybrid modeling, and three topics in there. So a lot of things which would be covered, which are tasks, nominated as tasks. I will leave you as your challenges. Okay, so just a reminder, if you want to find the location of the GitHub, you can go to my website, jacobcybulski.com, and from presentations, you can find this presentation, which is our workshop, and click on the GitHub, and you're there. Okay, so that's how you could find all the notebooks and also slides. Today I updated one of the two slides, two presentations, today's and the past. You may have noticed that on Discord, I was going actually through yesterday's comments, which were going through in parallel to my presentation, and some comments were very interesting. And there was one comment about I have this diagram with two block spheres, and I was talking about how your bad encoding could cause problems. And there's a tiny little note in there which says that even though all of the vectors on those block spheres are of length 1, but for the objective of better visualizing what happens, I shrunk some of them. So that led to some confusion among some of the participants. But there's a great comments, and I will definitely study your comments today. And normally when I give the presentation, I don't have time to look at it. But we have mentors who do a fantastic job. Tomasz Rybotycki, he did a fantastic job yesterday answering all the questions. So thank you, Tomek. Okay, so today we're going to start with a presentation as before. So let me just get to it. And hopefully you can see. So this is a session about classification with a gentle introduction to integration of pendulum with PyTorch. And then when we have the second session, we'll have a less gentle introduction. But this particular session on quantum classification it's got some intentionally embedded challenge, I should say, if not an error. I wonder if you can pick it up. Okay, so that little problem will definitely cause problems for training of this classification model. But let's see how it goes. So first, let's talk about what is classification. So when we talk about classification, we refer to the notion of a class. It's a class of a data sample. It's a group defined by some nominal value, which we call a label. For example, you could have a class for cars. The color of the car, that's red, yellow, green, the size, small, medium, large. So it has to be categorical variable. It is a process, classification is a process of classifying such data. And the whole idea is that if you see the new instance of that population, you should, based on its attributes, you should be able to determine which class it belongs to. So whether it's a color or size. So if we have a vehicle type, such as sedan, truck, and maybe something else, then basically the size and maybe the color could indicate whether it's a sedan or truck. So if it's red, the kid would say, yeah, it's a fire truck. If you're a bigger boy, you're going to say it's my sports car. But so you could actually predict the membership of some instance to a given class based on its attributes. So the classifier is a model predicting which class the particular example belongs to. And it could belong to many classes, possibly, and some class membership could be fuzzy. It could be based on probability of class membership. So that's in general. When we talk about quantum versus classical classification, apart from the implementation, the concepts are the same. When you talk about the different models which could be used for classification, logistic regression is one, support vector machines, then decision trees. It's a bit more difficult to implement decision trees using quantum techniques, but it's possible. Random forests, maybe not directly applicable to quantum modeling, definitely neural networks. KNN membership based on probabilities. Then we have Bayesian modeling, Bayesian networks, and of course, very more complex models such as transformers, which can be also implemented using quantum techniques. So when it comes to applicability of the quantum classifiers versus classical, again, we have some attributes of the population or attributes of the problem, which could hint on whether quantum modeling is perhaps more applicable than classical. So first of all, high dimensional feature spaces, definitely high dimensional in terms of attribute values, which could be better maybe represented in Hilbert space. Then the need for dimensionality reduction, possibly if we talk about few qubits. If you have few qubits, then it's a problem with multi-dimensional data. The issue of sampling from very complex distributions. Now, if we have simulation of some chemical properties and reactions, then perhaps the quantum modeling would be good. And then we could use also some stochastic problems, stochastic-based problem, like Monte Carlo methods. They have good similar models in quantum machine modeling. So classification, it's a concept that you should be very familiar with. Now, when it comes to data preparation, of course, when I give you an example, I'm going to spend quite a lot of time talking about preparing data for the classification task. One problem with quantum models is that because we have limited number of qubits usually to our disposal, maybe less now than a few years ago, so quantum classifiers are very sensitive to class imbalance. So what I'm talking about is if you have let's say a binary class, and one class is males, another one is females, and there could be a huge difference in the numbers in that population, then one class will be called minority class, another will be called majority class. The smaller one is a minority class. And classification in such situation is more difficult. And the problem also exists in classical classification. Now, in some critical cases, when we have a huge class imbalance, we cannot trust measures such accuracy. I'll give you an example. Imagine that 1% of population has a cancer. And that's cancer. So I'll set up a lab and I'm going to provide services, determining if from a sample of blood, I could see if there's a cancer present in this patient or not. And my method of processing blood samples will be as follows. I take blood sample, I flush it in the toilet, and I'm going to say no cancer. And guess what? I'll be 99% accurate because only 1% in population of people have cancer. So great, fantastic result, and very cheap because I don't have to do anything. So clearly, accuracy cannot be trusted as a way of determining the outcome of my model classification accuracy. If the class is balanced, then of course there is no issue. But if it's heavily unbalanced, that we have to rely on other additional measures such as sensitivity, looking the proportion of correctly identified true positives. So normally we say the class is positive if it's of interest to us. So let's say we find cancer in a sample. The class is negative if we don't find the cancer. So if you go to the doctor and they say, we assessed your sample and it's a negative result. Well, that's a positive news. The cancer is not there. So sensitivity, we look at proportion of correctly identified true positives. That means the people who have cancers, we detected a large number of them in the sample. And another one, specificity, is proportion of correctly identified true negatives. So that was a huge problem with COVID, that the early tests, they missed a lot of negatives or misclassified negatives. So people who had no COVID, they were considered as infected. And that is cost to hospitals, doctors, and so on. So there's other measures in accuracy. For example, there's something called Cohen-Kappa statistic, which unlike accuracy, it adjusts the measurement based on distribution of class values. So for example, kappa over 0.6 is considered good, and high accuracy but low kappa would be very poor outcome. So we need to think how to measure classification outcomes. So when we have a class imbalance, what can we do? So usually the classifiers perform much better when they work with balanced data. And so what we can do for the purpose of training the model, we could artificially balance the data. How can we do that? So for example, we could oversample the minority class. For example, we could replicate all instances of the minority class over and over again until we reach a certain level. Or we could undersample the majority class. So we could have random sample from the majority class to meet the size of the minority class. If you deal with 100 sample for training, then we have problems, of course. Balancing of training data could lead to better model. However, if you balance the test data as well, that leads to incorrect accuracy. So why is that so? Basically, the population has a different proportion of classes, and what we need to do is to work with the data as it is it's a real representative of the population. So we need to either work with proper test data as we selected it from the beginning, or we need to recalculate the measurements of accuracy to reflect the difference in the proportions. There's another method, it's called SMOTE, Synthetic Minority Oversampling Technique, and it's very interesting because it doesn't try to simply duplicate data in a minority class. It takes the minority class, or actually takes the whole population, and creates synthetic data, sort of data in between data. Yeah, so you could actually create random points which are equidistant from other points, and if it is the majority class, we reject it. If it belongs to the minority class, we accept it, and we include it in the minority class. So, so this is an interesting method, especially that it allows the classifier not to overtrain on the same data items over and over again. So there is a risk that the synthetic techniques may actually create bad performance too. So you always need to test whether oversampling, undersampling, or smoke technique, they actually make the performance better or worse. There's another possibility, which I've never seen done in quantum modeling, weighing data examples. So for example, by inverse class frequency, and some methods, especially in tree classifications, decision tree classifications, you could actually consider the weight of the data, which actually tells you which class. It penalizes data items which belong to the majority class. The decision tree algorithm could actually consider that in the classification process. I have some references here. If you work with Python, so the Cohen kappa, there is a good ready-made solution for you. It's a Cohen kappa which you could start using even now. And also the SMOT algorithm is available from another library. You could get it and start using it. Now, when we consider what we learned yesterday, it's still applicable here about analysis and preparation of predictors. Here we also need to prepare the target variable, the label, and we'll go through that in example. Here's an example of rebalancing your data, or rebalancing actually the measurements, the accuracy measurements after the classification. So imagine that we work with the population where we have 2/3 of blue class and 1/3 of green class. And to work with that, we're going to balance it so that we have equal sizes, 1/2 and 1/2. So we threw away 1/2 of the blue class. So now we create a classifier, and we have some results. So we have some false positives, true negatives, false negatives, true positives as outcomes of the classification and tests. Okay, so that happened on the balanced sample. However, the population is different. The population is what's on the left-hand side. We have a 2-to-1 proportion of data in the blue class and the green class. So what do we have to do? So basically, if we now scale back the proportionally the false positives and true negatives by equal measure, then we actually have the true predicted outcomes if we measured it in the population. So suddenly we know that false positives will be 1/2 of class of the blue class. The true negatives will be 1/2 of that class. So, and so on. So we can actually start measuring accuracy based on the rescaled proportion of data. And if you need to work with the confusion matrix, then again, this will be the outcome of our tests on balanced data, but the true confusion matrix for the population will be based on rescaled numbers. Okay, so that's a interesting approach. So if we know the prior probabilities, so prior probabilities are probabilities taken from actually from your original data or even from the population. It could be done independently of the sample you have. So sometimes for the purpose of statistics, they're going to send you balanced data already. So you could say there's 50% of males, 50% of females, but in the population, it's a very different proportion. So in such a case, you need to apply priors to your classification outcomes. How does it happen in Penelane and PyTorch? Okay, so some of you may be familiar with PyTorch or with TensorFlow or some other toolkit which could deliver some machine learning, maybe scikit or some others, or CP. Okay, so in PyTorch, we have to create a class. So on the left-hand side, we have a classical approach. We're going to look at the typical neural network structure. So this is the class of a neural network. And the class will, when you actually create an instance of the class, you could pass some arguments such as how large is your input, how large is your output. So talking about the layers, the input layer and the output layer. And then you could create your layers. So I actually have I separated a special method within the class in which I create several layers. So I have linear layers. I have my nonlinearity, the real function in between. And I have to make sure that all the sizes of layers, they match. So the input shape is going to match the linear layer. Then we have a result of that, which has to match the input to the next layer and so on. And eventually the last layer has to produce the shape of the output, which is exactly what is on the output of this neural network. So I can bring all those layers together, return them as layers, and then I could make them as a sequence, which is my model. Okay, there's other simpler ways of doing it. I'm doing it this way because I want to match it with what's going to happen in a minute using PennyLane. And every neural network has to at least prepare the forward method, which is basically a computational flow forward from input towards output. And in this case, it's very simple because we know that the neural network is going to receive input, and that input has to become, through the model, will have to map onto some output. In my case, I just use the same variable. It doesn't matter. So input is transformed through all the layers and to the output. Everything else is taken care by the optimizer, and that is going to act on the instance of this class. How would that happen if we wanted to incorporate the PennyLane model inside? That's on the right-hand side. It's very, very similar. We initialize the class. We could bring in all the variables as a local class or the instance variables. So such as the simulator, which is the device name, number of wires, number of layers, number of shots. Remember that for future use. And then, like before, I just say I need to have a function which will create the quantum layer. And in this function, I just create a model. I specify my device exactly as we used to do. I have my model definition. Either one of the methods here could give you definition or it's outside. So in this case, I have an outside definition of the quantum model, which is going to take number of qubits. And then I need to create the quantum node, the circuit. I need to specify that the interface for the quantum node is torch. In such a case that PyTorch will understand, sorry, not PyTorch, actually the PennyLane will rely on the format of data flowing in and out as a torch structure. And then I have to specify the shape of my model. So the data from the torch point of view, it's a black box, but it has to know what will be the shape of weights inside this black box. So we know the shape is so many layers, so many wires. I actually have a function shape like we did yesterday, which I can call. It will determine how many qubits, how many layers, and whether we have 1 or 3 rotations per qubit in a layer. Okay, so I specify the shape and call it weights. And now this is a crucial thing. Now I need to let PyTorch know that this model is an interface. There is an interface to this model called torch layer. So torch layer is part of the implementation of pendulane. And this will allow pendulane to understand that it's sitting within the torch structure. And torch will understand that this is some foreign module and will just pass data in and out. And what the optimizer will only worry about is that it passes weights to this black box in a specific structure as dictated by the shape. Okay, apart from that, I could have a utility function which could, once it's trained, it could return, and I could actually look at the quantum model which are built inside. So the quantum model will be built in a local variable model QC, which is a quantum circuit. And I can refer to it later on if I call this function. And again, I have a forward method which allows the computation forward. This example shows only how to create a single layer torch neural network. But of course, you can mix and match. You could create classical layers using torch specifications, like what you see on the left. And one of those layers could be simply the quantum layer, the quantum model, or maybe every second one. So you could have a sandwich of classical layers and quantum layers, and the weights and the gradients will propagate through them. So that's how we organize the structure. So what we're going to do in this particular session, rather than simply showing you how to build the classifier, I'm going to show you how to build the classifier which will live within torch environment. There's more code which I'll walk through. This is just to show that the training is identical for classical models and for models, hybrid models with quantum components. There's no difference between the code on the left and the right. So from the point of view of the optimizer will show no difference whatsoever. It's seamlessly integrated into the model structure of PyTorch. When it comes to cost functions or loss functions and optimizations, we simply start using the loss functions which belong to PyTorch. We can forget about pendulane loss functions and pendulane optimization techniques. We simply start using this full suite of, which is very rich, of different modeling techniques and optimization techniques which are available from PyTorch. Exactly the same happens with TensorFlow. So if you prefer TensorFlow, you can do exactly the same method. Okay, so another issue is how do we search for the optimum? And some of you may be familiar with it already. Okay, so the model has a number of hyperparameters. The optimizer has a number of hyperparameters. So the model hyperparameters could be number of qubits, number of layers, whether you use 1 or 3 rotations per qubit parameter, and many, many others, perhaps. The optimizer may have learning rate parameter. It may have number of steps it needs to execute. There is something called sigma, the actual precision of how you want to achieve. All of these are managing the whole optimization process. And a normal question is, what combination of parameters is best for this optimizer and this model together? So the normal method is trial and error, and that's a very inefficient method. A much better method is to have a systematic approach to doing so. So here is an example. We used so-called grid search. The grid search, it's a method of looping over a list of different hyperparameter values, constructing the model with those parameters, parameterizing the optimizer with selected parameters, running the actual model and collecting the training and testing performance, and then do it again using another set of parameters. And there's two different approaches today. Imagine we have only two parameters to worry about. So if we have two parameters, then what we can do is we could find maybe equidistance values of parameter 1, equidistance values of parameter 2, and then run a number of combinations. Parameter 1 and 2, this value and this value, and we could determine the cost function for it. The cost function is actually the three-dimensional, it's actually pointing towards us. So we have actually the three-dimensional map, which is arising from what you're looking at, and the projection on one side and the other side, if it's in the box. Those are the actual cost values. And what you see is projections of the cost landscape on one plane and another plane. Okay, so in this way, we could find, yep, this particular combination of parameter 1 and 2 gives us the lowest cost. So that's great. We have a systematic way of doing it, and it's very easy to do it within Python. And we actually could get some standard grid techniques to manage the whole process. There's another one, it's called random layout grid technique. Okay. Yeah, parameter, I mean hyperparameter. Okay, hyperparameter, which manages the optimization behavior and manages the construction of my circuit. Yeah. So this is not the training parameter in the circuit. Yep. So I need to stick to proper terminology. So we're talking about hyperparameter P1 and hyperparameter P2. Another one is a random layout grid technique, where instead of using equidistance combination of parameter values, hyperparameter values, we use a random distribution along hyperparameter 1 and hyperparameter 2. And as you can see, we can actually cover the whole area of possible combinations with fewer tests, because each point is a test combining hyperparameter P1 and P2. And we have much better coverage of that landscape, at least from the point of view of projecting onto those two planes on the side. So that's actually, it's a very good way of approaching the problem if you could create the random layout of tests. And again, I have here, there's a scikit learn hyperparameter tool, and there's a good article how to do it in PyTorch. Okay, so I mentioned before, we're dealing with accuracy. We're dealing with classification, and if we're driving the model optimization using something mean square error, well, this is good because everything is actually in continuous values, and mean square error could be your loss function, but there may be some better functions, because mean square error is more appropriate for dealing with continuous variable outcomes. We could try to drive it with accuracy, but accuracy is a very rough measurement for driving the optimization process. So there are better ones. So, for example, there's one, it's a binary cross-entropy measurement, which it's very good for optimization as a cost function, better loss function or cost function. If I talk about loss function, I mean it's a loss function applicable to a single measuring point. The cost function is when you run it across all training data or test data, and you aggregate your losses, and it becomes a cost function. Yeah. Okay. So if we run it through, we have on the left-hand side, we have classifier training performance. It's a cost function with mean square error to drive the optimizer, but we are interested in accuracy. And accuracy, as you can see, it's violently moving up and down. Whereas in the training of the quantum model, it gives you very smooth and very beautiful lines. And the question is it better? Well, it's a good question. We can see here that the testing accuracy for the quantum model is about 80%, whereas for this one, 73%. You can see here that the PyTorch gets overtrained very, very quickly. Okay, what does it mean? It means I haven't spent 1 minute trying to make this classical model any better. Okay, that's what it usually means. Okay, so just because I got my quantum model performing better, it doesn't mean I'm not going to get a better model classically, and usually I will. Okay, so we train the model. Now the question is, after training, can we improve accuracy? That seems like a bizarre question, but you can. So what happens is in training, we don't actually get the specific categorical outcome. Yes, it's a value of this kind or value of that kind. Usually we get the probability of the class membership. So what is the probability that this particular data item can be classified as here a red or blue item? And that means that now the question is, what is the threshold at which we decide what should be the outcome? Okay, so normally we assume threshold is 50%. So above 50% probability, it belongs to one class. If it's below 50%, it belongs to another class. But we could manipulate that. And so this is actually very interesting. So imagine that we collected a lot of examples. So those are the data items, and they were predicted. So they actually had a prediction value of, so it's blue and red. Okay. So now what happens is if we decide that the threshold is 0.3, that means the true value will be for those red and blue items, needs to be collected from, I can't remember, red is actually, which one is red? I think the red is true and blue is false. Okay, so those red ones are correctly classified items. The blue ones are incorrectly classified items. And here, the blue ones are correctly classified blue items, and this is the false negative. So from this, I could actually calculate the accuracy. But if I change the threshold to another level, then I will have a completely different outcome. So the question is, which threshold we pick? Okay, so maybe the one which is best in testing. However, there is another way. You could try to consider all possible thresholds of your classifier and construct a chart. This is called the specificity versus sensitivity, the false positive ratio, the true positive ratio. You plot the chart, and you could actually assess the performance of this classifier by the area under this curve. This is called the AUC curve, area under the curve. Okay, so and so that was invented during the Second World War when British used the radar and trying to determine if what they detect on the radar are enemy planes or birds or something else. And they had real difficulties tuning the radar. And so they decided to use this technique for radar tuning to determine the outcome. And so this way, actually, they have some fantastic results. There's a good question. Which classifier is better? Is the one which gives you the high area under the curve? That means it doesn't make a lot of mistakes no matter what threshold. Ideally, that curve should be square, okay, all areas. So it's perfect for each threshold, which is impossible. Or should we simply pick one best threshold? From the decision point of view, all you want is to get the best threshold for your data, rather than having classifier, which is good for all possibilities. But this is a technique. So what are the barriers to quantum classification? The problems is definitely, as with any other model, very poor encoding. It can lead to loss of information and biases. So solution is avoid simple embeddings and okay, and definitely you could consider trainable embeddings. We talked about that yesterday during the break. So for example, if very complex data, rather than using a simple embedding like rotational embeddings in RY or RX gates, we could use the whole model, trainable model, which decides what is the best embedding for your data. So for example, we could use quantum kernel. That's a very common technique that you could train the quantum kernel to give the best representation for your data, and then attach your quantum model or classical model afterwards. Definitely, the quantum models are very sensitive to imbalanced data. And so we have standard techniques, oversampling. We could also use hybrid classical quantum approaches if needed. We can hit barren plateaus, which they do exist in classical neural networks. They call them vanishing gradients problem. So it's a different name for the same problem. It's all to do with dimensionality. The solution to that often is regularization. You could do it via classical post-processing, or you could do quantum regularization. There's a variety of different approaches to that, like inserting random mid-circuit measurements, or injecting random rotations on qubits. So regularization could help overcoming some of the problems, especially with overtraining. Which is another one. The dimensional reduction could be used if you have too many features. One of the issue, which unfortunately is with all complex models, is that they converge no matter what data you have, except that you have rubbish results. And so they often get undertrained, but they converge. And so the plots look beautiful, but it doesn't work. Okay. So we have a demo here. I'll give you a demo of cars. It's one of the standard demos from UCI library, University of, which university is this? California, I think. I'll walk you through this. Okay, so let's so that will be in your notebooks. It's we have a classic classifier and quantum classifier. So first, I'm going to walk you through the classic classifier, which is just purely PyTorch. And they use the same data, and they prepare the data in exactly the same way. So the classical classifier is going to use the same range of values as if it was already preparing for quantum classification. So here is our description of the problem, and we're going to get the automobile data, try to understand it and prepare it. And this is just to understand that getting real data takes a lot of time in polishing it. So machine learning is no different. Analytics is no different. You spend 90% of time cleaning your data and preparing it for processing. So here's just general libraries and some of the utilities for plotting different things, which are in my utilities file. and PennyLane imported. Important thing is to import NumPy from PennyLane. I could import PennyLane optimizers, but only a limited number of different optimizers. Recently, PennyLane added a lot of more optimizers. But we have Torch, and a Torch, we're going to use the neural networking Torch. So I'm going to, well, here I have implementation. I say how many features, how many variables I want to retain from the data. Let's see the data first. So this is the UCI repository, and I get the data. It's ID10. It's that particular data set. So what we see in the data set are cars. And the cars, there's about 208 cars in this very tiny data set. We have the price, the consumption of gas, I imagine, on the highway, in the city, the technical specification instead of peak rotation per minute, horsepower, compression ratio, stroke, and so on and so on. Engine size, the size of the car in length, the wheelbase, and so on. And then whether it's a convertible or hatchback, whether it's the make and others. So there's a lot of different properties. One thing is to stare at it and observe, because then you can find interesting things. I can tell you straight away what is the interesting thing is that this data is already ordered. It's ordered by the label variable, which is the symboling. The symboling is assessment of the risk. Imagine we import those cars into Poland or Australia, and some guys are working in the port, and they need to provide insurance for importation, and or maybe even before loading the car on the ship. And they say, oh, well, this is 3. This car is very risky to insure, and this one is -3. It's quite okay. So what would be the risky cars? Maybe huge cars that during the ocean trip, if there's a storm, they were going to, the chains are going to break and they're going to slam and get damaged. So the symboling is a target variable here, and it's got values from -3 to 3. And if you carefully look at this data and your y coordinate, you can see that symboling is already ordered, and that could cause problems in our manipulation of data. But first, let's look at the data. The first thing I'm going to do, I'm going to make the life easier for us, and I'm going to select only numerical variables. Someone is sending things to me. I don't know if one of us, probably. Okay. Okay, let me know if there's a problem, because I can't watch what's happening on my other screen. The next question is, do we have any missing values? And yes, in this data set, we have missing values. Okay, so missing values, we can actually very simply determine that. And we have missing values across many different variables. So how can we deal with missing values? There's a lot of different approaches. I'm going to use the simplest one. If we have a column with missing values, I'm going to take all the remaining non-missing values in that column, and I'm going to take the average. And the average will be the value, the mean will be the value which I'm going to replace missing values with. But there are much better ways of doing it. You could use a model which can be trained to predict missing values in a data set based on other values which are non-missing. So having like a predictive model to predict what's missing, that's easy to do. In decision trees, that's almost like a default way of dealing with missing values. So we replace all missing values with the mean. And I check again if they're missing values. No. Now we standardize them so that every single variable is in the same range. So we have very different scale of different values. So some are 0, 1, to 9, 10, and massive values for price. And we want them all to be more or less in the same range. So I can actually check that visually. There's other problems with the data. You can see there is some variables are skewed, and that could cause problems. The price is heavily skewed. Horsepower is skewed, and normally I would have to deal with that somehow. Those of you who really understand regression analysis, then you really would be. It's the same technique is applicable uh, to managing variables for quantum or machine learning modeling. Okay, so now is the target variable symboling, what it looks like. This is the distribution. We can see we don't have any -3, so nothing is risk-free. There's a lot of things above 3. And the mean is somewhere here. This is the average, above 0.83. So what I'm going to do is, for the purpose of this exercise, I'm going to convert this label variable into a binary variable. So everything above the mean will be considered to be risky. Anything below will be considered risk-free. So that's a very simple manipulation, and this is my new distribution of my target variable with the mean slightly different. It changed. So now the question is, we still have a lot of variables. We have 17 variables, and if you try to construct on your machine, on your laptop, a model with 17 qubits, it's going to be very painful. So let's assume we will try to select only 5 best variables, 5 best features from amongst the 70. How can we do it? Well, you could use your intuition. So here's one. What could determine the risk for the insurer? Maybe the price, maybe how much petrol it uses. If it uses a lot of petrol, it's probably a sports car and very maybe expensive. So maybe it's a high risk car. Maybe the cars with a huge engine, which is, I don't know. That was my idea. So I picked some variables and I thought those possibly are high risk cars. But we could actually do some more insightful way of selecting variables. So here I select based on a number of possible statistical measures. So there's something like select k-best, chi-square, ANOVA F-test. Since we're dealing here with continuous variables, not categorical variables, well, categorical variables may be chi-square. If it's continuous variable, it will be segmented into bins, and then chi-square could be still applicable. Let's pick ANOVA F-test for determining what is the best set of variables to pick. So those are 5 best for based on a statistical analysis of my data set. Or we could use PCA, principal component analysis. And if I pick 5, it covers 87% of variance in the original data. It's a good coverage on those 5 variables. So PCA is definitely a good choice, except that we lost the original variables. So if you're not familiar with PCA, we sort of rotate my data into a new coordinate system. Unfortunately, the coordinate system is no longer original variables. They are random variables, and we call them PC0, 0, 1, and so on. Okay, so we lost them. We can still get them back because we're still dealing with the same records. So let's start with my hunch, and let's see what is the result. I get a lot of messages, but hopefully not for me. Okay. So based on, note that I'm copying it. So whatever was left behind there, it's a good idea to make a new copy of the vector rather than manipulate the existing vector, which something else could be manipulating. So I create a fresh copy of X and Y vectors. Okay, when it comes to my performance measures, like before, because I'm going to work now with the quantum models, I write my own. I have to use tensors, or at least square mean square error, because this measurement will be used by the optimizer. But once we put it into PyTorch, we don't need to worry about that because we can rely on Torch facilities. So those are the devices like we used before. So here I determine what devices I can support from the Torch point of view. So CUDA is a graphic card, and I do have a graphic card on this machine. So it does says, yep, I have CUDA, but I actually force it to use the CPU. Now, a good question which you may wish to ask, perhaps, when it comes to, okay, I'm still going the classic way. Yep. Okay, should we go to quantum way? I still go the classic way. If you run Pendulum with PyTorch and you have a GPU, what is better for you? Use a CPU, use the GPU for PyTorch only, and have a CPU-based Pendulum, or use Pendulum, which is GPU-based, and PyTorch to be CPU-based, or have both of them GPU-based? Okay, the answer is NVIDIA GPU, but it uses also GPUs on Apple machines as well. So definitely Pendulum supports Apple machines as well. There's actually others. So if you go to Pendulum, there's a whole website devoted to acceleration. Okay. So I use RTX, I think 490 or something like that, and it works fine. So the question is, if you put both of them working on the GPU, would there be any conflict? So I actually had problems running both of them at the same time on the GPU. I could run on Pendulum on GPU only, and in the past it was very slow. I was more successful running Torch on GPU and Pendulum on CPU, but it depends how much data needs to be shuffled between the two of them. So it's still experimental. I can't give you a good answer for that. Okay, so now I have some variables for PyTorch, but I'm actually running here classical classifier. So I use it only for data preparation. So this is exactly the classical representation with my layers. Here I show you in comment. Normally I would be doing it like this, but because I'm going to switch to Pendulum, there'll be Pendulum model here. So I isolate it in a separate method. But as I discussed in the lecture part, this is the structure. Here I create the test model. This is not the real model, just to find out whether it works. So I could move it forward, just give it, here, I can give it some test data. And I can also look at the structure of that model. So here's the structure of the model, exactly as is specified. And yes, I can move forward. So the forward method works. And here's the training. So the training is very boring. The only thing is that it's slightly different with the Pendulum because it starts with initializing all the gradients. Then we get the model, apply the model to data, calculate the cost function, maybe some accuracy as well at the same time. Usually I do it later. Then it's a learning step, and then optimize a step to the next iteration, and do a lot of extra shuffling of data and saving it. And so the training loop, it's boring. We create a proper model now, the model which we're going to train. I select cost function, which is not pendulum cost function. This is torch cost function. I use torch optimizer. Okay, so, and then I pass them in and train it. And it happens very fast. Okay, so I could test course calculated, and I have the terrible charts which I showed before. This is purely classical approach. Now let's look at the quantum approach. Okay, in the quantum approach, I do all the same thing with data. So I'll just start from the top and clear all the outputs. So getting libraries. Same libraries as before. Data preparation will be exactly the same. So I'll do it very quickly because we've done it. I have a bit more information just to show you that the class variable is sort of not random. So you have clusters of values together. So most of the safe cars at the end and most of the risky cars in the middle. So probably it's a good idea to shuffle it. And this is exactly the same preparation I've done before. The same thing with the label. I'll create the binary label, and I'll start with a hunch. Here I suggest let's do PCA, but let's do hunch to start with. I think that's what I called it, hunch. And exactly the same performance measures. I will not be using them anymore. Only if I wanted to test the model outside the PyTorch structure. Now, here I look at what devices, pendulum devices are available. Actually, there is not a simple way of doing it. So most of the people recommend do it in Torch, check what devices are on Torch. So MPS is actually for the Mac, okay? And hopefully you could pick the right device once you decide in Torch what is available. Okay, so I have a Lightning Qubit and CUDA, but I'll be running it on the CPU. Now, a lot of preparation here is exactly what we did yesterday. So we need to decide what is the size of the circuit in terms of number of wires, layers, what is the range of data. Now the epochs and other things will be now available for Torch. Preparing data. So this will be my model. It's very simple. Okay, it's as you notice, I have here this factory function which can generate my models given number of wires in here, number of qubits. That function, which will be modeling function, it's compulsory. It takes only inputs and weights. So if you want to have access within to any other variables, they either have to be global, or you could do it nicely and organize all of this in a function above. And again, I have a shape function which I create very close to it. The shape of this function, it determines the shape of the weights. And the shape of the weights is given by the entangling module. That's the only module which takes the weights. So I don't have to worry about to remembering what is exactly the shape, and I don't have to hard code it in my code. This is the structure of the class. This is the PyTorch class. Initialization, is a PyTorch initialization, but I can bring in the variables for the creation of my quantum model, which is the type of the simulator, the number of wires, the layers, the shorts. They are irrelevant to PyTorch site, but they'll be useful for the creation of my quantum model. So I save it as local variables. And as before, I just create all the layers, except that now I have a single layer here, the layer which is my quantum model layer, which will be developed. So I specify the device in terms of the simulator, the number of wires, the shots. Then I create the quantum node. So this is actually the quantum model first, and then the node from it. Specify interface to be torch. I specify that I actually have specific shape of weights to let the torch know how to manipulate weights and inside the model and the gradients, and then specifying that this is a special layer. It's a torch layer, which I return, and then I could actually incorporate it in my layers. Now, everything else, this is just a test like before. And you can see the structure is simple. It's only the quantum torch layer. And everything else is torch. Here only I show you that I can get the model out of the class. The training is exactly the same. The training loop is exactly the same, except it's slower. Okay, so that is something that you're going to see. It's slow speed. It's because we run on a simulator. So the simulator slows things down tremendously. Okay, so we have to wait here. We can use CUDNN libraries. Yeah, definitely. If you want to run it on a GPU, you need to set up the NVIDIA library, the whole CUDA toolkit. And in some cases, you will also need, especially for Pendelane, you need CU Quantum to be installed, QQuantum. And everything has to be very consistent. Okay. Now, I work with Linux, so I don't know if it's simpler or more complex, but NVIDIA is a huge installation. Okay, so do the scoring exactly the same as in the classical model, except slower. And yesterday you could see that I had within the loop, I was printing things. So that's a mistake here. I should have included the print within my loop to see if the system is alive or not. Okay, it finished. So I can plot the results. Okay, it looks better. It looks better. That doesn't look good. Okay, so that's 60% accuracy. The mean square error looks nice and smooth, but compared to this, I think that accuracy is better classically, no matter what. However, now we could play with this. We could see, yeah, maybe that was based on my hunch. Maybe the variables we selected were not representative of the sample. So that's actually a very important question. If we use a different selection of variable, or we use principal component analysis to select the principal components based on my variables, we may have a very significant difference. So let's actually do this. I'll start with PCA, but in your free time, you could try the other method yourself. Where is it? Here we are. So PCA. So I'm going to use XPCA as a method of selecting the variables. I'll just run the whole thing from beginning to the end. Now that hasn't changed anything, not the model, not because we could play with the model structure. Maybe the model is not large enough. Um, maybe it's got too few layers, too few qubits, and so on. The number of qubits here should correspond to the number of features. So at least that one is fixed in this particular implementation and coding. But you could have a model where the number of inputs is one thing, but you could have number of qubits much larger to have more parameters and more correlations between the qubits. Okay, so you have choices there. You can see now in training, the accuracy is now 86%. It will be interesting to see what happens with testing. But that was a very important aspect. Is it's all in data preprocessing, and here we have well, accuracy 88% was in training. Oh, sorry, that was accuracy in training. No, scores. Okay, so 88% accuracy in training. The testing scores are still ongoing, or 89% actually. So this looks like a terrible life of people developing models, because you want to be clever here, and you spend all the time doing dumb things, preparing and cleaning data. So eventually we have accuracy 78%, which with compared to classical model is better, but the classical model could also do the same choice, and I bet is going to beat us. So if we have here XPCA, and we start from start to finish, and this will finish very quickly. It's still thinking. Okay, that's good. It's not as quick. And you can see it improved in charts as well. Why don't we get such smooth action? And that's because possibly we use which optimizer we use. We use Nesterov Adam optimizer. So it's got the second momentum optimizer, and it means that it has some sort of stochastic element to it. And so we have here accuracy of 1 eventually, I think, in training, and 89% in testing. Now, can we improve it? We can improve it tremendously. And one way of improvement is one thing we could add classical layers to it. Another way of improving it is to look at what we produce as in terms of measurement. I need to be finishing because it's okay. I mean, just checking the time. 20:45. Okay, now we still have time. Okay, so what we return from the quantum model as a result, it's expected value. Okay, expectation value is returned as a measurement. Is that the right measurement for classification? So we have values from -1 to 1. Okay, if you have any comments, you could put them into your chat. What will be better, the probability result or expectation value result for classification? Yeah, almost Definitely probability, yeah. So you want to know what is the probability that this particular data item belongs to one class or the other class. And so that is common sense, because that's how classification is defined from the beginning. When the model is trying to determine which class it belongs to, it looks at the probability of those two possible outcomes. So clearly, this should be probability measurement. But then we have an interesting problem, because that means the result of that model will be not a single value, but two values. We have probability of two outcomes, 0 and 1. And somehow this model has to deal with that. And it can't deal with it simply by taking only half of the measurement, because we will be losing half of the um, of the information, even though we know we lose the information we could deduct. But from the optimizer point of view, we're losing also information which it relies on in the optimization, looking at the cost landscape. So in this case, what will be required is to actually attach to it another layer, which would take two inputs and produce one output to convert it to a single value coming out, and then return the result. Okay, so another question is there a way of producing a better shape of the outcome from the classical model? So this is titled somewhere logistic regression, I think. Definitely the next part of it will be looking at the same model and trying to figure out if what we can do in this part, in the forward step, can we somehow shape the outcome of this model? Now we're looking at hybrid models. So now we have two concerns. One thing is what we do in a quantum model, what type of results it returns on measurement, whether the classical model has to understand what data comes into it. It has to be exactly the same size and shape. Okay. Also, whatever input comes into quantum model, the quantum model has to receive it in exactly the same shape. So the flow of information between your classical layer and your quantum layers must be consistent. The problem is, for example, if you have a global measurement, so you measure all qubits and you measure probability, and suddenly what it results is exponential size to the number of qubits. And so the classical layer has to receive so much data. So you need to think about it, that the consistency between the communication between the classical component and the quantum component need to be very clean. Okay, so also the errors you're going to get now, it will be errors coming from your quantum modeling and from classical modeling, but it's worth going through this because the hybrid systems are definitely the winning solution for quantum modeling. I have a few more minutes, but I probably need more time for the next session. So in summary, what we did yesterday, we were looking at just the basics of quantum machine learning. Then we moved into estimation. From the point of view of modeling, it's not much difference between classification and estimation in terms of the structure of the models. In terms of measurements, there is a difference. When it comes to hybrid models, things get much more complicated. But one of the first examples I'm going to show you is that the hybrid models in Penny they are beautiful. They're beautiful because you could mix and match different types of computational elements. So as long as they could be considered functions and they're differentiable functions, and the gradients could flow through them, they could be optimized in exactly the same way. And so you could have hybrid solutions which could be readily deployable into your client's environment. So if your Python and Torch are deployable, therefore your hybrid model with PennyLane is deployable as well. So it's a very seamless integration of the quantum solutions with a standard environment that a lot of people have on the sites. So that's actually we're at this stage, and there's a lot of tasks here. It's worth going through them, and the next stage will be we will look at the same data and to start with, but I want to spend on the challenge problem, and I want to walk you through the integration of functions and matrices and classical and quantum components as well. So there'll be challenges for you to research how to convert your probability outcome from this into a mixed set of layers. There'll be classical and hybrid and quantum layers, and how to catch the probability into the classical model, and then how to actually squash it so that we're going to implement sort of logistic regression. And that means it's a better fit with cost functions which are designed for logistic regression. Because that's what we're trying to do. We try to actually, the quantum model generates probability as a linear function because everything is linear, but then you have to convert it into your logistic regression function, and that works better with classification. A big challenge will be, can this data, which actually started as a multi-labeled data, multi-class data, can you fix that model so that the quantum model returns a multi-value class, and we could, whether we can or cannot implement the multinomial classification system. That's probably for those people who are already well versed with machine learning or data science, and you're familiar with PyTorch or something similar, because it's all to do. Most of it is to do with the classical process, post-processing. Okay, let's have a break. We have half an hour. And after that, we get into the really advanced stuff. Thank you. So I'll go and clean my carpet after I spilled my drinks all over the carpet. Okay.
Okay, thank you. Thank you, Jacob.
Yeah.
Thanks.
So we're now starting the last session on advanced methods and looking at hybrid methods in particular. I'm going to start with continuing where we finished. So I mentioned some issues with the model. In particular, we had expectation value as a projective measurement on the z-axis. And while you were away, I played with it to change it. So we're now returning probability, which is measured on a single qubit. Okay, so that will probably require a different loss function, which happily we have the whole range of possible loss functions in Torch. One of them is the binary cross entropy loss function, which is perfect for this type of classification problem. So basically, let me just restart kernel from the top and clear, and I'll walk you through. So everything above is the same. This basically, I'm going to slowly get you into thinking hybrid and thinking how you need to meet one problem with one issue with another. Okay, so we have here is the same structure of the model. We have a different measurement. It's the same shape of weights, so there's nothing to change. And the changes will start here. So now what happens is that now we'll be receiving not one value from the measurement, but two values. So it's a probability of measurement 0 and probability of measurement 1. And we know they are one minus the other, so why having both? That's how it's returned. So the problem is that it seems to be the simplest thing would be when it's returned like we had before. In the forward section, we just take half of the measurement and return it. Well, this is wrong because we're losing half gradients. So the optimizer will not cope with that. So what we need to do is to taper measurement. So I'm taking two measurements, have an extra layer, which will convert it to a single measurement, and then we could play with it in the forward section. Unless you want to return two, in which case we need to design it differently. So what we do here is I'm going to create an extra layer. I call it linear layer 5, which take two input, one output. So now I can create the model. So that's a quantum model. And the layers will be the quantum model, which takes input as designed for by this torch neural network. And then there'll be this extra classical layer, which takes two values and returns 1. Okay, that seems to be simple. What I'll do next is I'm going to replace how I'm going to do post-processing of it. And if I return simply the model as it is, I'm going to give a linear model. The linear model is going to have problems with meeting the values 0 and 1. So we're going to use sigmoid transformation of it, which is suitable for logistic regression. So those of you who, I think that everybody should know this in this group. If you've done data science or machine learning or physics, you would know what I'm talking about. So people from science background, you leave regression, and logistic regression is not a problem. So now we're transforming the output with a sigmoid function. So as a test, get the logistic regression. In fact, if you ever do this without this extra layer, you're going to have problems because you're going to produce two values and then you try to return 1. And there's a lot of inconsistency, which usually they pop out in applying cost function, not exactly in the place you expect it to. So this is just a test to see what we get. So the test looks good. We have some inputs of this type, the labels 0 and 1, the results, yep, they look like probabilities. And now we have a different structure of the model. It's a sequential model with two layers. One is it's a quantum layer and a simple linear layer, taking two inputs, producing one output. So the quantum model looks the same, so there's no difference, except we have just one measurement. That function closure, that's necessary for more complex optimizers such as LBFGS. And they have internal loop which the closure can support. I'm not going to use it here, but if you wanted to test it, the closure is required for running the model, optimizing the model with this type of optimizer. You can actually use the closure with Adam and Adam optimizer. So here nothing changed. The training loop the only thing I'm going to change is use a different cost function, BC loss. Oh, I'm using here, this is just to show you how you use LBFGS. And where is the closure? Well, we could use, oh, here's the closure. Make closure, but where is it? Okay, I don't see it. I don't know if it's going to work. Oh, I passed the closure inside here. Okay. So this is actually, I'm going to run it with LBFGS. I haven't noticed that that's what it is. So a different optimizer. And this closure is passed to the training model. So the training model will use it. We'll see how it works. Okay, so I'm getting high accuracy, 91% now. Scoring the model. And we have different curves. So now it looks like the training iteration is less because this particular optimizer has got internal loop. So it looks like it requires fewer iterations, but they are external iterations. The internal iterations are not shown here. However, we can see that in training, we have a BC cost, no longer mean square error. So that may not be meaningful to us, but in accuracy, the training accuracy went up to 91% and maximum accuracy is 78%. So it's not as good as a classical model, but you notice that how quickly it finished. So we could possibly require either more complex model or more time. I don't know if you noticed how fast it was running. So the speed of that was, first of all, because I picked a better, um, it's a better shape of my outcome. And secondly, I used better suited cost function. So also addition that of the single classical layer, it sped up the whole training. So we can see benefits right away, even though it's a very small addition. One other thing is you may want to have more complex models. So this is the overkill. So it's a complex model of lots of linear layers. And here we have the quantum model at the end. And this linear conversion. So let's see if that model would work. I included it already. I called it Easter egg layers. So I'm going to comment these ones out. Let me just see how it was done. Yep, I'm creating that quantum layer. I hope it's going to work. Haven't tested. So now we can see much more complex structure. The quantum model is still the same. Everything else the same. I think the training accuracy went down, but maybe I need more epochs. Okay, so we improved the accuracy. The test accuracy went up. So we can play with that. Now it's we can see how sophisticated is my model. We have multiple layers. The quantum layer is shoved somewhere in the middle. Now, when you construct such a thing, a good question then anybody should be asking is, what happens if we remove the classical layers? What is the performance of the model? What happens if you remove the quantum layer? What's the performance of the model? And the question really is hybrid model better than pure quantum or pure classical? And compare those three. And so there's a lot of papers out there which say we have a hybrid model and it's fantastic, but they never compare what happens if you take the quantum model out. Would that be still better? Okay, so that would be an honest approach to using quantum machine learning. Okay, so you need to be basically a data scientist, and you need to provide the best solution, regardless if it's quantum or classical. Okay, so that example, there is actually quite a lot of tasks you can still do. You could play with it. I showed you how to include the closure, and the closure is, I have to check where I plugged it in. I think in training, the closure is used in training model. Yeah, closure. So basically, if the closure exists, it is, okay, so here is the optimizer step is different. If the closure is required by the optimizer, then the optimizer step must include the closure. And the closure is basically performing all those steps separately, except that the optimizer has a lot of extra tasks which is done outside the standard structure of the optimization steps. So the closure is to provide all the standard steps for the optimizer to do it when it's appropriate in its algorithm. So one classical algorithm which always needs it, and it's very difficult to find out how to use the closure, is LBFGS. It's very efficient optimization algorithm, and you could see how fast it was running, and it gave tremendous results. But without closure, it will not work. And if you look at examples of what people do with the closure, they are horrid and almost impossible to find out. Okay, so that takes us to the next interesting thing. Here is another example. It was shown as a S0 example. So I show you here an example how you could mix and match different type of entities into penny lane structure as facilitated with torch. So you can do it in pure penny lane, but it's much harder. So imagine we want to create a function of that type. It's a function f, which takes two data sets, and one data set is processed by circuit 1. Another data set is first processed by a function, and then circuit 2, and then the results of both are input to circuit 3, which then is transformed by a matrix. Okay, so there are different types of things here. So there are data sets, there is functions, there are circuits, and there's a matrix. Here to simplify things, I replace the matrix with a linear neural network. Okay, but it's a single step to use torch matrix multiplication. So how do we go about that? It's quite simple because you've seen all the steps already. So I'm going to create some dummy data. So we have data 1 will have 3 features, data 2 will have 5 features. And of course, the number of qubits or wires needs to reflect the sizes of data. And the circuit 3 will have the number of wires, there will be one stream of information coming from circuit 1, another stream of information from circuit 2. So it will have the number of wires which corresponds to wires of both circuits. I have devices created for each circuit separately because they have different number of wires as are required. Let me just make sure that okay. I define 3 circuits. So this is what you've seen already. I use a decorator. It's just a quick way of doing it. Just make sure that we use the interface torch because we are going to integrate it with torch structures. And here I create the glue between all the components using PyTorch module. So this is my hybrid function f. In the initialization, I'm going to create first a simple linear transformation, so creating function 2. So I pretend function 2 is just linear transformation, but I could actually be applying a normal function here. The second thing is that the final matrix is emulated by a simple linear transformation. I could simply use torch mul matrix, I think it's called, or mul mat. So here I have actually the torch layers, which are hiding away penny lane models. And my forward movement is just creating everything one after another. So branch 1 of this structure, I have here branch 1. Data is taken by matrix 1. So the data flows in. Branch 2, we have data which is transformed by function. This is the result. And then that result goes into circuit 2, this result of circuit 2. Now we're joining circuit 1 and 2, which is now I merge them together and to create the input for circuit 3. The input for circuit 3 goes into circuit 3 and then out. And then it goes through another transformation, the matrix multiplication, which could be replaced by, if we have actually physical matrix, we could plug it in here. And that's it. So suddenly I merged all together and just creating 2 data items using mean square error loss, using Adam optimizer, and running it. So here, it's a dummy data. It converged. You can see it actually improved. And now I need to apply this model. So I create, again, some testing data, random, and use the function as if it was normal function. And this is the result. Okay, so you can see that we could put together a very complex structure using quantum components and classical components of different type. In fact, you could even get chips interface to it, hardware chips, and run emulation of hardware chips as functions. So that's the beauty of penny lane. I'm sure you can do it using other platforms, but maybe it's harder. Okay, that takes us to the last part. And the last part is the challenge, but it's also a lecture to talk about more complex quantum models. So myself and Sebastian Zans, who is our mentor here as well, we worked on a number of projects on quantum autoencoders. And so this talk is to cover quantum autoencoders. And why quantum autoencoders? Because they are the models which demonstrate the beauty of quantum machine learning, which cannot be replicated with classical modeling. Okay, I think I got some. There's a conversation between Thomas and Maya. Okay. All right. So let's get into it. I'll talk about the architectures. I'm going to look at specific quantum encoders, explaining what they are and what you can do with them. I'm going to look at denoising quantum encoders, looking at encoding choices, selection of cost functions, ansatz, and others. And looking at some tricks which you can do. And then I'll walk you through an implementation of quantum autoencoder. So what are they? They exist in classical machine learning and in quantum machine learning and in deep learning in particular. And basically, the architecture is of this type. There's some input data, usually tabular, but we're going to show you here how to apply it to time series of signals. There is encoder of this data into a much smaller space. So there's a compression of information on input into what we call latent space, the hidden space, which is compressed information here. So because it's compressed, something has to disappear. So the whole idea of a well-functioning autoencoder is that the compressed information contains only the essential information from which you could recover most of the useful information. So there's a decoder, and then if you decode it, you should get on output, if not identical, but very close information which was on input. What you want to lose in the middle is things like noise. So if you plug in here a noisy, a scratchy photograph, you could train autoencoder to remove scratches. Scratches are noise, and what will be retained is just improved photograph. We applied that to removing noise from signals. So you have a noisy radio signal, and you could process it and have an improved filtered noise. Now, filtering of noise from signal, it's done by engineers for years, and so that's nothing special. It's very hard to compete with normal standard filters, but it's a good exercise for writing an autoencoder. Okay, so this is the structure, and this is what they do. Why quantum autoencoder? Because they, first of all, it is an interesting application. It does something that is normally done in reverse. No, usually you apply quantum encoder to blow up dimensionality into high dimensions. And here we want to do the reverse. We want to compress information. So it's just the opposite way. The training is difficult. It's a semi-supervised learning. So yes, you show what you want to expect on output, but in quantum models, you don't need the entire model to train it. You could only use half of it to train it. It's very bizarre. It is good for processing high-dimensional data. So you could have videos and other things on input and then squash it in the middle and compress it. Barren plateaus could crop up and you could have difficulties. And let's actually see what you can do with it. We're going to apply quantum encoders to removing noise from signals, and applications are many. In the past, I worked on machine condition monitoring. So you have big industrial machines, and they have a lot of rotating parts, and you could actually record the signal over time, and you could spot problems with the machine, which show as changing frequencies of rotating parts, or the noise emerging. There's new frequencies appearing. So that's one application. You could actually apply it to sales of beer, sales of any product. We have a lot of seasonality, and you could look at the different brands and then compare, looking at the correlations between sales of brands. So one thing which we discovered is that small brands in USA, they don't spend a lot of money on marketing. They simply do what big brands do. And if big brands put a lot of beer on the market because there is the final of American football or basketball, they also put beer on the shelf, because and people want beer, they want any beer, not necessarily the expensive one. You could use it for in seismology and many other applications. So that's actually interesting. You want to filter out noise and look at the essence of the data. Heart monitoring in particular as well, weather forecasts. The time series could be univariate or multivariate. We start here with simple ones, the univariate time series, just one variable at a time. There's usually some seasonality oscillations and so on repeating over time. So there is some repeating pattern. And there's lots of challenges in quantum time series analysis. It's high volume of data. Data ages quickly, so the old data is no longer useful. The values within the snippet of data that you could handle at the time, it's a sliding window of a time series. The values here are not independent. So unlike the tabular data, where the data, individual features, you want them to be orthogonal, here the values are highly dependent on each other. And the other problem is that the consecutive values, the neighborhood values in a time series are usually very close. So once they get mapped into high dimensional space, they tend to clump together and cluster together. And they call it, it's a problem of homogenization of features in high dimensional space. So there's a lot of standard methods of dealing with that, statistical methods, highly effective, but they need a lot of data preparations. So it's very strict conditions imposed on with the data. You have to ensure the data is stationary. Usually you need to reduce dimensionality, you need to aggregate the data, imputation of missing values. Of course, we have to do the same. Removal of noise. We actually don't want to remove the noise. We want to remove the noise and identify it in the process. And you have some conditions on the normality and homoscedasticity and so on. So there's a lot of preparations to be done, and quantum machine learning methods are more flexible and have less preconditions. But the same is for classical machine learning. So we're going to look at ability of quantum autoencoders to reduce noise in signals. That's our primary objective. And we will be using at the time series, the sliding window protocol. So this is not a curve fitting problem. It is actually trying to determine the patterns in data from the temporal context, from the context of that window, regardless of where it is in a time series. So it's a harder problem than, if you remember what we started with was time series, but it was relationship between specific position on x-axis and the value, whereas here we actually look at the patterns of data in a window in isolation. So here is a possible problem. We use synthetic data, and this is what you can possibly do. So here's a lot of noise in this data. It's about 20% of Gaussian noise. You can see the dots are noisy dots. And the noise here is injected artificially. And this is a sample signal here, the true value of the light blue. The noise are actually, this is what the autoencoder sees, is that those dots. And this is actually the prediction of what the data should supposed to look based on that noise. So it's almost an impossible task. But we generate a lot of noise at every iteration of training. So each time he sees different types of noise, and from that could predict what the data should look like. So this is what happened in training, and that's what happens in testing, and it's not bad, considering how difficult is the problem and how severe is the noise. So that's what a quantum autoencoder looks like. I called it the monolith architecture, and that will be obvious in a minute. So we have here data on input and has to be encoded. So we encode noisy data here. On output, we want to have recovered pure data, clean data. And in the middle, we have the quantum autoencoder encoder component, which encodes the data and input into compressed latent space. It discards some part of the information in a trash space. And so to ensure that the data doesn't flow any further, those qubits get initialized. And then from the latent space, there's a decoder component which decodes data into quantum information, and on measurement, it should give pure data. So that's a typical structure. Okay, so that looks like a normal model, except that it's got this narrowing in the middle. Now, what we hope for is that what is trashed is noise, and what is the essential information about the signal is actually in this component. That's great. Okay, so the question is, can we trash it? Can we reinitialize the qubits in such a way that it is the whole model is still unitary, or we cannot? So actually, if you perform a measurement at this point, this becomes a nonlinear transformation. So this is not a differentiable model. Okay, so once you have a mid-circuit measurements, you cannot actually differentiate that using penny lane. So that's bad. So can we replace it with something else, which would ensure there is information stopped at this point? And I'll show you the technique for that. And a typical training will be like anything else. We get the result in training, the difference between what's expected and what's produced, and optimization of parameters of the decoder and encoder should take place. And the data that was presented as pairs of noisy and pure data for the training. Okay, so the main issue is here the nonlinearity, because with nonlinearity, we will have difficulties training it using penny lane only. There's no problem with training it on PyTorch. But I'll show you the other technique. So that's latent space trash, a typical terminology. Not to be confused, this encoder with data encoder. Okay, so this is the encoder of data into latent space. That's embedding of data in a quantum circuit. Now, in training, actually what we do, we artificially inject noise into training, into pure data. So we present pure data on input and output. We inject the noise, and we train the model to remove it because we know exactly what to get on output. Okay. Now, this is the mystery of quantum approach to this. So let's start with a simple example here. Imagine that we're going to train this model to recognize on output what is given on input. And so we have a decoder. We actually have decoder and encoder is the same model, except that the encoder is a reverse decoder. That means it's back to front. It's actually the adjoint of the decoder. You can see this adjoint. So what does it mean? It means that regardless of what are the parameters of this model, because that's an inverse of this, the data that flows through this and gets encoded will automatically get decoded if there's no trash space, if all information flows through. You get that? That's an important point. So if this model is an inverse of this model, it completely, every operations in an inverse, and it just reverses everything. There's no loss of information anywhere, so the information gets fully recovered. The only thing at the end, what needs to be done, you need to actually invert the output, because otherwise you would get the inverse of this, whatever was given on input. Okay, so that's easy to understand this part. Now, we try to do the same thing. We just use pure data. We put the pure data in, and we increase the trash space. So what's going to happen? So if you just don't train this in any way, obviously we're going to lose some information in this area, and there'll be some noise creeping in. So that seems to be like an obvious thing. Okay, so to be able to improve this, what you may want to do is to start training the parameters of that single model, which is inverted on the left-hand side and in here. So you could actually train it. And that should be able to improve it. And possibly you could train it in such a way that you reduce the amount of information lost, and most of the information or meaningful information will flow through this part. Okay. Now here's a trick, which is actually a beautiful trick. Since we know that decoder and inverted decoder, which is encoder, is the same model. So is it possible that we can train just only one instead of training both of them having the same, they share the same parameters on both sides? So we could create the following structure. We feed in data on input. We have parameters of the inverted decoder here. You'll be training those parameters. The trust space is going to be measured. And there's a latent space which we ignore. Now, what we're going to do, we're going to train the model in such a way that we lose minimum information on those trash qubits. So what happens is in a quantum model, information never gets lost. Okay, so if suddenly those qubits become zero, that means all the information must be flowing through the latent space. This is at the moment, this is the unitary structure. It's a unitary circuit model, which means there's no loss of information anywhere. If we could train it in such a way that we get zero on trash space, that means all information is in the latent space. Okay, so we train it until we get as close to zero in trash space as possible. Then we put it back in, we invert it, and we suddenly train the whole quantum autoencoder using only half of it. So this is like an unbelievable thing that we can actually do such a thing. Okay, so that's actually something that you cannot do using classical approaches, because you don't have, first of all, you can't invert computation easily. The second thing is that classical models lose information. Okay, so in quantum modeling, we don't lose any information as long as we use unitary operations. How about the noise? Okay, we're going to use the following trick. We're going to train the decoder the way we've done it a moment ago on pure data. So inverted decoder learns to recognize pure data only. It learns to float as much information as possible through the latent space and minimum information through the trash space. What do we do next? The next thing is we invert the decoder and put it back here. And because everything is inversible, it means that if the same data that was actually flowing through this, which is actually compressed pure data, will arrive at this decoder, it will actually convert it into pure data. Well, that's interesting. Okay, so we trained it that as long as this information, it actually matches the information, compressed information of pure data, the decoder will do the job. So now what's left to do, we freeze the parameter values of the decoder. We put encoder completely new. It's not a mirror structure of that at all. We put a decoder here and train it on noisy data so that we actually get zero at the end, so that everything gets canceled. So if we put if we put here the clean data and we trained it perfectly, we would arrive at clean data at the end. And actually reverse of the clean data at the end, inverted data, and we should get zero at the end. There's nothing. All qubits should be zero. So that's what we're going to do. We're going to train it by feeding noisy data in such a way that when we actually measure it, so this is now inverted data structure, it's going to flow this way because the decoder would be required inversion of it to produce good data. So at the end, we should be getting, if we put inverted data at the end, we should get 0. So that's the training of the encoder, and we have a full system ready to go. The question now is, if we want to do it in a pure quantum way, can we actually do something about the mid-circuit measurement? So if we actually want to measure it within the torch environment, it doesn't matter. But if you want to do this in pure penny lane environment, this will not be possible because it's a nonlinear situation. So what we can do, we could actually use so-called control swap. This is actually called the swap test. We could add additional qubits with zeros on them. And we can, so this is actually in this stage and as well as this stage. So this actually, sorry, for training half encoder, we could do so-called the swap test, and we could monitor this phase kickback effect. So basically, it swaps the values of one qubit with that value flowing through trash, and we could actually monitor the state of that single qubit for training this situation. If you want zeros to appear here, we don't need to actually measure anything. We just add qubits with 0, and we use the swap operation between the trash qubits and 0 qubits, and basically there's 0 flowing into the decoder. Okay, so there's actually a way of getting rid of all mid-circuit measurements and measurements for the half encoder using either swap test or using swap operations here to get zeros in the trash. In which case, this becomes a pure unitary circuit and could be trained with arbitrary penny lane optimizer. Okay, so this is what the circuit would look like for the entire circuit. So this is actually the full circuit. And the example I'm going to walk you through, I'm not going to do the tricks with half encoders, but that's a possible way. I'm going to train all parameters in one go. There is actually the benefit of them, because in this situation, if we have a decoder trained on minimizing the trash space and we freeze these weights, that means we don't have a full ability of looking all possible values for the parameters of encoder and decoder. So the performance is not going to be as good as the performance in a full structure, which each parameter is independent. However, in this case, we have double the number of parameters, and therefore the complexity of training is much, much higher. The complexity of the training is, it should be linear with the number of parameters. However, because we use the simulator, it becomes, I think it's exponential complexity here. So you have more parameters. This becomes very slow to train. In this case, each time we train half of the encoder, we deal with half of the parameters. So the performance is much, the training performance is much quicker, but accuracy will not be as good. So how can we, this is what it looks like. We have, I can actually invert the structure. So even though the parameters are independent, I could mirror the structures so that in ideal situation, without any change of the parameters, when I initiate them, it will automatically reproduce input on output. And here the middle part, which is the trash space initialization, I add additional qubits, which flow 0, they initialize to 0. And at this point, the values simply get swapped between qubits. The trash qubits and the 0 qubits are replaced. And the measurement at the end. And if you want to measure the amount of information lost in the process, you could actually measure the remaining qubits. And you could actually measure how much information was lost, which is not flowing through the measured qubits. Now, if we wanted to move into hybrid quantum autoencoder, we have now millions of possibilities. Okay, so we could actually have one half could be quantum, one half could be classical. Both could be classical. The hybrid, the latent space could be quantum. But in this case, I simply have two half quantum autoencoders and have a layer in the middle which links them, which is the latent space. It's a classical layer, and maybe at the end, the measured qubits, it's a classical layer. And that actually, it accelerates the training tremendously. What is the problem with that is that normally when information flows through qubits, the amount of information flowing through qubits is much, much higher. It's exponential amount of information that flows through qubits, the quantum model, full quantum model, than through the classical layer. So we lose a lot of information here. All phase information is lost. So the measurement is on some, let's say, onto projective measurement on Z axis. And so we lose phase information at least. Okay, so the loss of information could be significant. So we have to test it and train it and see. You have to actually perhaps use measurement, the rotations appropriately to lose the minimum information at this point. But we want to lose information. It's just how much information we want to lose. It's a big question. So here's the example of training on a sample of time series. So the model gets trained on this part. This is just one of time series, the clean data, this one section. And here is recovery of information for that data. And you can see amount of noise which was injected during training. It's huge area of noise. So, and this is just one example of noise which was used in recovery for that particular curve. It can be still improved, but it's interesting how much information can be improved from such noisy data. So this is also a challenge for you. It's a lot of extra work for you guys, and challenges are not required to do the quiz. The challenge is for you to extend. A lot of times you do hackathons and other things, and if you want to apply some of the knowledge you learn in this workshop, we have tasks that is worth doing, and then you have challenges which can extend your ability to apply this knowledge. This is hard, but this is what we can do. So we use this so-called monolith. That means we train quantum autoencoder, encoder and decoder together in one go. That means it's a lot of parameters, and that means that the training is slow. So if you have a big machine, go ahead with this. If you have a small machine, if you have a laptop, you have a lot of time that the laptop does nothing else, but it just works on this. As a summary, okay, first of all, what quantum autoencoders can the classical autoencoders cannot do? As quantum unitaries are reversible, it's possible to train only half of the quantum autoencoder to gain full quantum autoencoder for functionality. It may not be as efficient as training the monolith, but it's possible. Okay. There's a lot of claims that just doing that part, training on half, it removes noise, and I could not actually confirm that. I had always better results training the the monolith quantum autoencoder. And we had some interns over the summer, and we were actually testing this, and we have some data. We were going to publish this. The second is this: the quantum unitaries don't lose information, so it's possible to train quantum encoder on to flow the relevant information via latent space, but minimizing information flowing into trash space. So in a quantum model, if information is redirected, it's never lost. It has to appear elsewhere. Okay, so that's actually an interesting phenomenon, which does not exist in a classical sense. Okay, so this is like water, pouring water into the basin with two outlets. If you plug in one, the water has to go the other side. So this is, we called different models. It's monolith and stacked of two half encoders. We also have something called sidekick. You could actually train those models not necessarily on the latent space in the stacked model, but you could actually train as two half autoencoders which get correlated via latent space. So we had other architectures for quantum autoencoders. But your job will be, first of all, explore very chaotic data time series, Mackey glass data time series, understand the current pure penny implementation, but make sure this already is ready for PyTorch. And you're going to adapt it and change it and improve it and then score the pure quantum encoder and then rewrite the pure quantum encoder into hybrid quantum autoencoder model, including PyTorch, and then compare. And the next question is, you may be lucky because the quantum models are very sensitive to initialization. So if you change the way you initialize them from the very beginning, you may have very different outcomes. If it's a random initialization, then perhaps you should do several of such models for different initializations and only compare the final mean or median effect. Okay, so we could generate 9 instances of differently initialized quantum autoencoders and then score them and produce the model, which is model of median performance. Okay, so that's a challenge. I'll just walk you through this. And here is the challenge. Okay, so same libraries as before. I use Penelane. I haven't included here Torch yet, or maybe it should be. Maybe it appears later on. Oh, yes, import Torch. Sorry, got it. So the Penelane, NumPy from Penelane and Torch. I use scikit-learn for processing a matrix, and I rely on the utilities in another of my utilities from Windows to be able to split data into sliding windows. I have some debug information, so I'll just put here 1 so we could actually see some additional information. Okay, the first thing is that quite often in Torch, you need to specify what type of floating point numbers you're dealing with, and you can do it once and for all. Specify upfront. You say default data type is double precision, floating point 64 bits. Okay, so we're going to use that. You've seen those functions before. And we have a very, very long data preparation. You've seen a very, very long data preparation in the previous session. So here is a different data set. This is the Mackey glass time series generator. So It's difficult to figure out what the parameters means, but you could ask some AI to explain it. But here's a specific combination of parameters that will produce data of this shape. So you can see it's not a sine function, it's not regular, it's got some oscillations and a lot of random effects. And you could make it much worse. So that's the beauty of this generator, that if you play with those parameters, you get very chaotic data, which is difficult to train on. So a lot of people working on quantum machine learning models use about two different types of synthetic data. One of them is Mackie glass. The other one is NARMA. Okay, so we're going to decide on the split of the data between training and testing. So the 2/3 of data will be used for training, 1/3 for testing. The window size, so we here have, how much data we have? I don't know how much. Probably 300 or 600. Oh, you have to find out later. Maybe it's 200 data items. Okay, so window size will be 5. So there'll be small windows floating, and they will not be floating one step at a time, but just 2 steps at a time. So there'll be overlaps between windows. I'm not doing predictive modeling, so here's the horizon. Looking to the future is irrelevant. We ignore it. The noise is 20% Gaussian noise and random seed. So the first thing is that here is a function, a help function, which will take some x and y coordinates, so which was we just produced x and y, and we split that into the training and testing data and inject the noise uniformly into the entire series before we split it into windows, and then turn them into tensors. Okay, so this does everything that's required. So at this point, if we call this function, so create sliding window tensors, I apply it to x coordinates, and because y coordinates for my problem are identical to x coordinates, because we want to get an output what I got on the input, except that I'll be injecting noise into data on input, and I will do it here only for the purpose of plotting, but I will do it iteratively so that the model is not going to learn a specific type of noise. If I inject the noise once only and train the model will fantastically train to learn this noise and will never learn any other. It will never actually give you correct results on other types of noise. So during the training, at every iteration of training, I'll be creating different noisy data on input. So here I just show you that's how I'm going to do. Like I'm going to create x and y coordinates, and I'm going to add noise to data on input, but not on output. And if I want to plot it, because the windows overlap, and during training the individual windows, the overlap space will have different values. So I need to do something about that for plotting. I need to collapse it back into flat structures for plotting. And so I'm going to average those overlapping areas, and I have a function for that. So this is what data looks like. It's the same data as before, but now it's split into windows and the noise is floating around. Okay, so this is the data we're going to deal with. Okay, so now we're thinking about the actual structures for the quantum model. We're going to rely on just the standard structure. So we're going to assume, yep, we have windows of time series, but let's treat it as normal data. So that is it. Suddenly becomes just a normal problem. because the only thing we have to remember, we never shuffle the data because when shuffling makes no sense anymore. The data flows in time, okay? In a normal application, you perhaps would be having a large window of data, which is the data for you to consider in training, because all the data is obsolete anymore. So we need to remember that in time series and signals, all data, it's no longer relevant. Okay, so I have some parameters for the quantum autoencoder. I have the latent space. The latent space is how much data flows through. I know that the trash space is basic number of qubits minus the latent space. So I can window size actually is the same as number of qubits. An interface will be torch. And I can also specify differential method. You could use adjoint. It's actually adjoint works well with Lightning qubit. If you use best, the pendulum will figure out what to use. So I'm going to use Lightning qubit. It's written in C++. It should be much, much faster than default qubit. Okay, so we've seen this before. We have the shape. Now I'm going to provide here the shape of half of the qubit. But I know that the shape of the entire, sorry, not half a qubit, half of the quantum autoencoder, but the shape of the entire autoencoder is double. So I'm saying is double number of layers for the entire autoencoder, full autoencoder. And here's a bit of calculations, what this should look like. And I wrote some helper functions to for encoding, the sequence encoding at the input, the shape of the entangler, and then the entangler itself. It's all local functions so that it looks like a class, but this is just pendulum. And here's the structure of full quantum autoencoder. I bring in all the non-local functions, non-local variables from the parent function, the factory. And I just build it one piece at a time. So I have a input sequence, then barrier, calculate the shapes. If someone gave me incorrect shape, I reshape it to what it's supposed to be. Then I know what is the shape of the encoder. I know what is the shape of the decoder. Then if I receive weights, because eventually this is supposed to get, where is it? Its input is weights in inputs. So if the weights are received, somehow I need to say some of those weights belong to the encoder, some of those weights belong to the decoder. So this is split here. And I create the encoder ansatz, and then create decoder ansatz. And optionally, if I request it, I could invert it, the adjoint. And eventually, I measure all qubits in the data wires, because I have more wires. I have also 0 qubits in there somewhere, because the 0 qubits, the swap space is separate, and the data doesn't belong there. The data belongs only to the latent area and the trash area. Here are some tests performed. So this is just creating a small versions of data for testing and then showing what it looks like. So this is a small version of the entire quantum autoencoder, which I built. But here's the real model. So simply I create using all proper variables for number of latents, qubits, number of trash qubits. If I need any extra qubits, I will add them to create more parameters, how many layers, and what type of rotation I want to use, whether it's only Y or rotation or XYZ rotation. And create some sample parameters just for plotting. And now create the circuit and create the node and eventually drawing it here. And you can see it's all parameterized. When I create the node, I specify what is the interface as declared. So the interface is torch. What's the differential method, and whatever it was. Okay, so it's adjoint. So that's actually very efficient for the simulator. If it's a quantum machine, it's a parameter shift method, which is the only thing that works. Okay, so it's a training loop which trains with noise. I have the closure here, but I don't use it, so I just include it. If I wanted to use it, we have an example in the other notebook. And I start here by creating pure data. So I just create pure data at the very beginning, and then in a loop, every iteration, every epoch, I create different noisy input. So I know what will be on output. The noise will be created each time, 20% of noise. And if I want to plot this noise ever, I just add it together with the history of parameters and the history of costs. And because I'm using torch tensors, so I need to do a bit of gymnastics here. So gymnastics is like stacking tensors, simple appending, and eventually finished. So this is the training loop with noise. And this is just standard torch defaults. So we have initial weights, we have some random weights, we have Adam optimizer, mean square error loss, and I'm ready for training. And the training, it will take time because this structure, this particular model, it has a lot of parameters, and this is quite a lot of complexity. I can't remember what is my number of epochs. Let me check it. Number of epochs is 200. Okay, I should have started with 50, but that will give us some pretty good result, I think. You can see it takes 30 seconds for 20 iterations. So that will take a few minutes, okay? So this is the challenge. It's an interesting challenge because you can see the model is complex. It's got not only complexity, this is just pure quantum model. I'm not using any of the hybrid effects. The only thing I've done is to use proper torch tensors, and so that I could train the model using actually using which ones? I'm using the torch optimizer and using the torch mean square loss. So this is already interesting because even though I'm not using the overall structure of torch class, I can actually use the torch facilities for training the quantum model. Okay, so that's actually an interesting approach, even though I'm not using the structure, the class structure. I can train penny lane models using torch facilities already, which means it's much easier now to restructure it and put it into the torch neural network class and perhaps add layers as required in the challenge. And that was here. So that we add an extra layer in the middle. We need to create additional measurements in the middle. So those measurements are over the latent area. So you need to be able to interface this quantum model with that little latent space. They need to meet the size. So ideally, it's expectation values measurements. And then this new Hall decoder, it needs to take as many inputs as there's classical elements in the latent space, and then produce as many outputs as there is inputs of the classical layer. So there's a bit of complexity here. It's not a lot of work, but there's some complexity, which it will really exercise the ability to go through this whole mass of code and trying to encapsulate it in a larger torch structure, but the structure which is very flexible. You will also have to provide all the glue, which you need to turn this into a separate model and declare that this is a torch layer. This is a separate model, declare it as a torch layer, and then put them together into a larger structure. So that's your challenge. I don't think it's a challenge. It's very hard, but it will take maybe a day's work. And this one is still training, but I think it's nearly finished. Or maybe it did finish. No, it's still going. It's another 20, but it's 200 overall. And you can see it's not gaining a lot of, it's not knocking a lot of cost off, but we'll see eventually what it looks like. So this is the history. You can see a bit of zigzag here, so there's a bit of noise. And I select the optimal training model. So ideally, we should be getting the optimum test model. And so I selected the optimum, the best model amongst all models trained by the optimizer, whatever was saved into the parameter list. And you can see that already it was able to remove a little bit of noise from training data and quite a lot of noise from test data. And how is it measured? Basically, it's the difference between just pure data and noise alone versus pure data and whatever data was recovered from noise. So the signal, which is compared here, it's completely recovered purely from noise, so from noise only. Okay, so eventually this is what it looks like. Okay, so the dotted lines, this is the signal recovered from noise alone. We pass in that severe noise and it still figures out what it is against the truth that is behind. Okay, so that is, it's a 10:15 only. Okay, the challenge lecture. I did very fast everything. Okay, so that actually takes us, maybe have some questions that I could go through. Any questions? Because I'm happy to.
You can also raise your hand if you have some questions and would like to
I'll
unmute. Sometimes it's easier.
okay, I can't actually see the hands up. How do I see that?
We do not have any hands raised, so that's why you do not see them.
Okay.
But I just
Okay,
said that people can do it.
I'm happy to answer questions. Questions about the whole workshop activities, because we have about half an hour at least to do that. Yesterday, we had a lot of interesting questions which appeared on Discord. And we have a couple of very active people asking questions. And let me
And by
just...
the way, Jacob, I can see that Thomas is doing really, really great job with answering all the questions on the chat. So perhaps this is the reason why people do not have more questions now, because all the questions have been probably already answered by Thomas.
Yes, yeah, Tomek did a tremendous job. Well, we have here a lot of knowledge. There is we've learned about quantum machine learning in general. We've learned a lot about penny lane, and I think that it's very difficult for you to grasp all of it in 2 days. But what I hope we achieved here is that you get confident that you could build simple models, and you can see there's very high level tools which I use constantly. Things like I don't have it. I just share it again. So we have ready-made templates for building models. Okay, so here we have things like basic entangler layers, strongly entangling layers. We have angle embedding. You will see that sometimes I need to remember at the very beginning, I talked about passing big data into a model, and then we use broadcasting of the parameters. And in this last model which we built, this is actually being used. And you can see here that I am actually passing the entire, where is the cost function, the model. Okay, so here I pass the entire tensor of noisy data. So not individually, I don't get one window at a time. I pass the whole batch of them. And the model, because the model is written using those standard templates already deal with that. So they actually ready for broadcasting. And so the only difference is that now when I receive it back, you may remember if I do the measurement, I received as a list for each measurement. So I had to do, you need to just pivot it around into the correct order. Okay, so so that's already happened here, and maybe you didn't notice that it was actually quite fast for considering how much data I use here. We got it in a few minutes. If we were doing it one window at a time, it would take much longer time. So this time, because the data was already broadcasted against the parameters on input, this was actually done much faster. It also was a C++ qubit, so it's much more efficient. If you have a GPU, it will be interesting to see how fast it works on the GPU. At the moment, my machine has a broken NVIDIA setup, so I have to use CPU. So this is actually here you can there is evidence that broadcasting can be actively utilized. And if your input is defined using the standard templates, which is in this case angle embedding already knows how to deal with a table of data, and there's nothing else to be done. If you were to do it by hand, you would have to write, you have to consider slices of data specifically for batched input. Okay, so that we solved it easily because we relied on the standard angle embedding feature, which comes from the Penny library. Now, if you missed the the first day. You perhaps don't know what I'm talking about. But one of the exploratory notebooks, the very first ones, which is a tiny model, it explains the difficulties of passing more than one record of data into the model. Sorry, more than one record of data. If you just pass one, there's usually no issues. If you must pass more than one, unless that model understands there's a batch of data, you are in big trouble. And one thing which is actually worrying is that you will not know you're in big trouble because the model is going to get trained. It's going to get trained on maybe two pieces of data from your big batch, and everything else is ignored. And you'll see that the model's not learning at all. And it's very hard to spot that. So if you ever have the situation that you create the model, you optimize it, and because there's evidence the model's not learning, zero learning, that's actually one of the very common problems that you're broadcasting incorrectly or you're broadcasting accidentally. Okay, so most of the data is lost in that process. What else is in this code? It's one thing is that it's worth to do this systematically. I know when Tomasz, our mentor, he looked at my code a few months ago. He said, "Terrible code, terrible code." So I'm not a programmer. I try to make it neat. It's only a notebook. It's you need to think that if you were doing it properly, this will not be done in that form. You would write a proper modular code in Python, and notebooks are not necessarily the best environment for development. Okay, so it can be done better. But some of you are probably better software engineers than myself, so you're welcome to correct me. Anything else? I think that one other thing is how to think about this noise, because that's quite often as one of the regularization could be to inject noise into data rather than the model itself. And so that's another lesson here, is that that ability to create extra noise in data, that's very convenient for a lot of applications. So if your application struggles, it could be overtraining very quickly. And so adding noise into data can help as well. And you just have to remember that you cannot add noise once. You have to add noise as the process of training is happening, so that the model is not learning the noise itself. Okay, it's a lot of. I had fantastic results, which actually went to a conference paper. Fortunately, that's not the version of the paper which eventually was appeared, but I didn't realize I was actually the model was learning noise was giving me fantastic results. So that's one thing, is noise has to be added while training is happening, so that it's different types of noise each time. Okay. I wonder if nobody has any questions about this mini example. Perhaps I should get a proper matrix here, but it shows how you stitch very complex structures together. And if you had to do it without the help of PyTorch, you would really struggle. Okay, so PyTorch is fantastic of putting things together in very complex networks of interconnected models. Okay, so that's not only for neural networks. So everybody thinks, yeah, this structure is for the module. It's a neural network structure. Now you could, it's a functional structure. So you could have functional, non-sequential models built that way. I wonder if many people here. Oh, we have Mateusz who wants to talk. Mateusz, you have questions?
Yes, yes. I have a question. So actually a couple questions.
Mm-hmm.
So in front of me, I have a Sieci neuronowe do przetwarzania informacji by Stanisław Osowski. This is a book. In English, it is Neural Networks for Information Processing.
Yeah.
This is by Warsaw University of Technology. It's in the first few chapters, there are mentioned different neuron types.
Yeah.
And one specifically caught my attention because it's called Grossberg neuron. It's instar and outstar. And
Mm-hmm.
what it does is that it rotates the state, the vector, and it tries to replicate the input vector by an angle after normalization step. So what we do is pretty much when we normalize a vector, what we get is as an error, we get a cosine of phi. So like the difference between the let's say difference between the angles in the space, multidimensional space, it doesn't matter.
Yeah.
And I wanted to know is this is mostly how we do our, let's say, quantum machine learning. This is like we try to replicate the input vectors, and the closeness to the input vectors, based on other rotations in our network, is the mirror of fitness. Is the actual like fitness of our, let's say, model that we try to make.
Yeah, I don't know the Grossberg. I know that I've read Grossberg's book from 1980. But I'm not sure what is the exactly purpose of that rotation. Whether it's a form of regularization so that you could create some artificial error by tilting. Is it tilting individual neurons or is it tilting the whole layer of neurons?
It is like a single neuron in the network, so it can be entire layer can be composed of these. This is like a building block.
So this is actually on input,
this is
or
like a replacement of sigmoidal or perceptron neuron. It's a replacement. It takes the input vector as let's say x1, x2, x3, which is kind of like an observable in the space, multidimensional space. And what it tries to do is you pretty much perform an inner product, what I can see from it. And in the terms of when you normalize it, your amplitude is 1. So it basically simplifies to the cosine of two angles. And it tries to approach. Again?
And this activation function then, or?
Yes.
Yeah. Okay. So probably it's the single neuron would act like what happens in a quantum model, but then there's benefit of having that activation function, which is nonlinear. So I imagine that there's some similarity here, definitely. Yeah. But I would have to look at it in more detail. Yeah.
Oh, okay. So yet another question, and I think this would be a final one.
Yeah.
Can we just let's say, use 1/2 of our encoder-decoder network as as encoder, and just use the output, measure it in the reduced space now, and perform a classification based on this actual. Let's say that we perform a classification based on this encoder.
Okay. Let me just
right?
Okay, I'll put slide on. Okay, where is it? Sorry about that. I need to say slideshow from this. So you're saying you want to perform classification on whatever is compressed, yes?
Yes, exactly.
Okay. So in a sense, you could train it. You could train the half the encoder using, say, this method. Okay. So and then you could you say you could, instead of classifying based on the full data, you classify already here. Yeah, it's a compressed compressed representation of what's on input completely. So absolutely you can do that, and that's actually one of the applications of autoencoders in general, is that you could train autoencoder. It doesn't matter in what way. And once you get the parameters of the encoder and decoder, you could drop off the decoder, and then you could simply use the latent space as a compressed version of your full data on input. Okay. Then you could do the other thing, is that you could drop the encoder and you could put random data on in a latent space, and it will generate some data on output. Okay, it will hallucinate data on output, and that's actually the principle of how GANs work. That the GANs work is like autoencoder, except that the latent space is used to generate random data. Use the decoder for that purpose, and then you put the what's now is encoder on the other side. Okay, so GAN is just an inverted autoencoder. So that's actually an interesting thing, especially if you trained on pictures. So if you get a picture and you get a good picture on the other side, if you then remove the encoder and start creating dummy things, you're going to get some pictures on the other side. Because that's whatever appears, it's a high quality autoencoder. The latent space, it's a full compression of your input, and you ideally lose only unnecessary noisy component of your information input.
How do we deal with phase information? If we would like to let's say use the latent space, so we need the decoder back, right? Because the decoder could also
phase information
recover
flows
the
here.
phase.
The flows here. If you measure this using classical method, you lose that. So phase is something that you lose in the process of measurement, in computational basis.
Mm-hmm.
So that's actually one of the problem. This is the benefit of using swap test. So what happens, let's say you want to minimize loss of information on trash. And if you measure the trash, you measure information without the phase. So you lose information already here. But if you use the swap test, and the trash could be large. So basically you concentrate all of the information in your trash into a single qubit. So the measurement, you still lose phase information there, but you measure a single qubit. It's an easier measurement, and it's considered to be higher quality measurement. You lose less information in this process. Okay, so this is actually measuring classically, or normal measurement here. You lose a lot of phase information in that process. So that's why when we train the entire model, that phase is preserved. It's flowing between encoder and decoder. So there's no issues of losing phase at this stage. And the measurement is for the purpose of determining whether the output generated is what's on input. Because the input is classical and output is classical, and your function, your cost function is classical, that's not an issue. But the important thing is that you preserve all full information in latent space, because that was an idea of training on empty trash, is to flow all information back into latent space. And we don't know exactly in what form it is. Okay, we know it's compressed, but if all information which was classical is now converted into quantum information, the phase is actually containing a large part of information, which you don't want to lose.
Okay, I think there are some other questions by Mr. Arkham. So thank you for answers.
Any questions? I know the Binvu was asking lots of questions yesterday. Any questions? No? Okay. So now it's the question, what's next? And summarizing the workshop that was took 2 days. There was a lot of learning, and what I hope you got is the basic fundamentals of quantum machine learning. You understand the structure of quantum models. You understand the implications of how information gets converted from classical to quantum and back. What part of information is usually lost in the process, but only in measurement. The fact that there is this unitary model, unitary operation, which means if you build your circuit of standard operations like rotations and normal gates, they are usually unitary gates. So if you put them together into a larger model, you get a unitary operation as a model as a whole. The only thing is that if you reinitialize some qubits in the middle or measure qubits in the middle, okay, there's some question. Okay, I don't know. There is some. I think that Tomasz was putting things together. So if you get the if you create measurement in the middle, you're going to lose information, and it becomes non-unitary and non-differentiable. So that type of circuit will not be working with penny lane. Some types of penny lane optimizations. If the circuit is non-unitary, you could still measure it classically, and you could perform some classical optimization on it. I have a lot of questions here, which I can answer. Okay, so we have some recommendations of papers to read. Definitely there's a good paper on re-uploading of data, which was Maya found on Discord, and she provided a reference to this. There was actually, I remember there was a really good, definitely the book by Maria Should. You should get it. There's some papers, a lot of papers by Maria Should, which are worth reading on archive. So that's great. And I think that some of the papers aged. So I remember that the knowledge of quantum things, they age very quickly. And Maria wrote a lot of papers, say 10 years ago and more, and the technology moved on. So there were some papers on neural networks and whether every model is a kernel model, and whether every so there's a lot of claims of that kind, or any model is Fourier transform. I think that those papers are aged a little bit, but she's got fantastic papers, and the book is great. So we have here a lot of interesting resources which were added in the process. Okay, so yeah, so it's a great a list of resources that Tomasz Robotycki is recommending. He collected them all in one place. There's also another great book. He says it's by Aldo Faisal and Cheng Sun Ong on the basic of machine learning from MIT. So coming back to the summary, so he's actually typing wildly here, summarizing things, which is great. So you can do it in your infinite free time. We've done some exploration of estimation, and estimating models are one of the easiest. I actually found that classification models are much harder. You may have noticed it. So dealing with continuous observations in the type of models we explore was very simple. When we deal with classification, we have to do a lot more. It's harder work, and when you move to hybrid models, we get a lot of help from the facilities available in Torch. But you need to be very clever about it. So I would really recommend trying to complete that session 3 or that big example I showed you at the beginning of the last session, when you put together the hybrid model and you start looking at logistic regression. Okay, so this is really utilizing the power of Torch, which is not existent in just plain quantum models. Okay, and the final thing is that we have a lot of interesting work, like with the QIE is only one type of model. Last year we talked about different type of models. We looked at reservoir computing and quantum reservoirs, and that's actually another fascinating area, which again, hybrid models where the quantum component is responsible for developing the feature map in high-dimensional Hilbert space. So the whole idea of the quantum component is to blow up the dimensions and into high dimensions and randomly initialize it. There's no training involved in reservoir computing. Reservoir computing has completely random model, which combined with very simple ridge regression, it gives you incredible accuracy in performance. So that's something that it's, again, worth exploring. There's a lot of interesting things which we could do with quantum modeling, which can be done in classical way. So classical reservoir models work incredibly well as well, but we utilize directly the quantum model's ability to shift data into exponentially high dimensional space. So there's opportunities, and you will probably not get advantage in quantum modeling simply by taking a classical model, applied, converted to quantum equivalent of it, and applied to classical data. There is zero chance that you will get any quantum advantage from that. Most of the models which I showed you in this workshop are in this category, unfortunately. Maybe except for the quantum autoencoders, because they bring something new and unique, which can be done only in quantum models, but not in classical ones. So you need to think about what are the quantum model facilities? What are the facilities in quantum computing which can be taken advantage of, which you cannot gain from your classical machine learning? And that's actually a hard way. There's some areas where opportunities readily exist. Opportunities to do with the complexity of data, like or the close proximity between the quantum effect and the phenomena in real life, like in chemistry, in physics, in high energy physics. This is where the quantum simulation really helps. Apart from that, we need to start thinking about new algorithms, and perhaps the algorithms which come from the variational quantum algorithms in the future will have to change. So at the moment, we still apply classical approach to optimizing quantum models, and there are definitely better ways of doing it than this. However, at this stage of our knowledge, what I believe should be happening is that we need to learn how to manipulate the elements of quantum models. We need to learn how to even replicate classical models and learn where they go wrong, why they go wrong, what can be improved, and tinkering with those quantum effects is something that will give you some new insights. Okay, so I find that I'm learning all the time. So and I use my friendly AI agent as my research assistant, as a and also as a as a person with whom to debate some of those things. So actually, I use my AI for that purpose, rather than for writing my code or models. So that's actually interesting. It's a new learning experience, and I hope your experience was positive. And there's a lot more to be done after those sessions. There's a lot of tasks that you could undertake. There's challenges for you, and if you get stuck, don't hesitate to send us your questions on Discord. I would like to see that this Discord server becomes our contact point for the future, and definitely you should be able to ask us questions. And if you have any interesting results from any of these exercises, please put them in. And if you get difficulties, you could get help not only from us, but from other participants of this workshop. Okay, so at this point, I think I'd like to give my microphone back to Pavel, who could possibly give us some closing.
Thanks. Thank you very much, Jacob. So first of all, Jacob, thanks once again for giving this wonderful workshop. I believe that all the participants have learned a lot and will learn even more after watching the recordings and taking the quizzes. So regarding the quizzes, we'll share. I think Jacob, I think we can already share the link to our Google form. Yes. So we'll do it just soon after we close the Zoom.
We can spoil Sunday.
Yes, regarding the recordings, I think we'll try to publish the recording from yesterday today, and the recording from today's session hopefully tomorrow, but we'll see. Well, definitely it will be in a few days, maximum a few days. We just want to just process the videos. Alternatively, Jacob, if it's fine for you, we can share the link to the unmodified version of the recording directly on the Discord today, and then we can start working on the processed version for YouTube, which can take a few days. So it's up to you, basically. If you
sure, absolutely.
we can do it. Yes, yeah, because okay, all right. So we'll yes. So we hope that the recording from today will be also today, hopefully. If there are no technical
half an hour
issues
of silence.
Yes, if there are no technical issues with Zoom, then we'll probably have the recording ready later today. Today in Europe, of course, because I know that it's quite late in Australia already. All right, so I think this is all from our side, and I would like to join Jacob in thanking Tomasz as well for his tremendous job as a mentor. He really answered all the questions on that we had here. So that was fantastic. Great job, Tomasz. We would like to thank all the participants for coming. I was impressed that we had almost 500 signups. Yesterday at the beginning there were more than 120 participants. Definitely a few hundred people joined our Discord server. So there's a huge impact already given by this workshop and Jacob and Tomasz, of course. So this is great. We are very happy. I will also later share with you a feedback form. This is our second workshop. We are planning to organize similar workshops in the future. So we will welcome any feedback you can give us. Yeah, and once again, thanks everyone, and I hope that everyone enjoyed this time and we all learned a lot.
Okay.
Thank you.
Thank you.
I'll now stop recording.
Okay. So good luck, everybody.
Good luck.